Animals, earlier animal dung were providing carbon, and traditional sources of farm nutrients are not there. Compost, crop residues, green manure. So natural sources of organic carbons are reduced as such. Now what sludge does? It improves physical, chemical and biological properties of soil, improve textures. Due to increase in biological activity, nutrients are in the lower depth of the soil are made available to the plants, provide major nutrients required by plants, increases water holding capacity of the soil and minimizes evaporation loss of moisture from the soil. So, but just by using organic manures or carbon source, soil properties is highly benefited, and which is helpful for increased growth or increased fertility of the soil. And some common sources of organic fertilizers are farmyard manures, green manures, vermicompost, biogas slurry, biofertilizers, city compost. And now one more category we are trying to add into the book: hygienized enriched dry sewage sludge as biogold. So already this is there in government gazette, these sources, but this was not there. Fecal source was not there. Now it is being added to the gazette. Now if we see, we can see that organic carbon in city compost is only 12%, where in treated sludge is 20 to 40%. Farmer manures, animal dungs, is 20 to 30%. This can provide nitrogen 18 kg per ton, phosphorus 2 kg per ton, potash 3 kg per ton. Pathogens are anyway absent, whereas in farmyard manure it is present. And then we talked about plant growth promoting bacteria. In the morning also somebody talked about it. So if we inoculate untreated sludge or non-irradiated sludge, the PGP growth is only 3 into 10 to the power 9. And when we put this plant growth promoting bacteria in treated irradiated sludge, then the 100 times more growth is there. It is just like making yogurt. When we make yogurt, we boil it and then add culture, and a good curd is formed. Same way, when we irradiate, most of the bacteria are killed. So the new bacteria grow very well, and their growth is about 100 times. So US EPA 40 CFR 503, their guidelines are there that presence of pollutants like arsenic and all those things, they should be in limit. The presence of pathogens, they have given guidelines. The sewage sludge attractiveness to vectors, e.g. rodent, flies and mosquitoes, etc., they should be met. So then it forms a biosolid A, and this is what US EPA says. Now we see that STP process is aerobic, anaerobic digestion, chlorination, centrifugation, sun drying. They help in meeting the US EPA. Irradiation also helps. Inoculation with PGPB also helps. Bagging. I mean, if you bag the sludge, hygienized sludge, then its shelf life is quite large. Concentration of heavy metal, I have already discussed that. Although it is there from city compost, US EPA says 75,000. I mean, US EPA limits are very high. Whatever we are getting is much low. You can see US EPA says 7,500 milligram per kg, but we have only 212 to 720 per kg. So these limits of our sludge, I mean, that every city has to analyze. Industrial city will have more heavy metals in their sludge. So maybe we have much lower sludge than USA or Britain, and this is maybe you can say it is a boon for developing countries to have low heavy metals in their sludge, and they can use it in manure. So I have already told that how we can control. We have to either control the polluting source, minimize the use of sludge, increase efficiency of sludge by PGPB. So if we use PGPB, we can reduce the quantity of sludge to be used for agriculture application. So we have integrated this PGPB technology with sludge hygienization. I think any microbiologist within a year can develop this kind of formulation to be treated and put along with the sludge. Now, once we have to sell the sludge, it should have some specification. And sludge is so variable in chemical composition that we cannot set any fixed composition. So we have made some specification which are minimum, like moisture maximum should be 25, bulk density less than 1, total organic carbon less than 15, although it is minimum 15, it's maybe 20, 30, but we have kept some minimum standards, pH between this. So if the sludge is meeting this criteria, then we can use it for agriculture sports, like heavy metal as per limit of US EPA. Our heavy metals are 1000 times less than US EPA. But still we have kept this as a thing. And then biosolid air norms, pathogens, PGP not less than 10 raised power 7 spore or cyst per gram of dry sludge. So 10 raised power 7 spores are already there. They will not allow other bacteria to contaminate it. The value of health benefits and environment protection cannot be calculated. I mean, you can use it, but there are indirect benefits which we cannot calculate. And we did lot of field trials before we could use this treated sludge with PGPB in Anand Agriculture University nearby this facility. And we tried on tomato, wheat and potato. And we can see 100% RDF. RDF means recommended dose of fertilizer. I mean, if we grow potato, tomato, there is some recommended dose of chemical fertilizer. So when we put 100%, this is the kilogram per hectare, the crop yield 29630. Now if we put 80% of recommended dose, the yield goes down to 27,000. 60% we put, it goes down to 25. Now what we did 80% of RDF plus 20% of biogold. The yield went up to 31,000 from 21 to 31. And this is the true with all tomato, wheat and this thing. So what we observed that if we use biogold, then we can save 20% on chemical fertilizer. And other thing, the yield has increased. So this really helps with 1 ton per hectare, that we get 20% saving in chemical fertilizer and more crop yield. So these experiments we did on 25 meter square plot, and earlier also we have done a lot of research on this area. So finally we can conclude that 20% reduction in chemical fertilizer at 1 ton per hectare use of bio NPK treated sludge. So that's how you save and increase the fertility of soil. Now we checked how much heavy metals migration is there from soil to the crop, like tomato. So same way we did 100% chemical, 80% chemical with biogold and irradiated sludge alone. So you can see that cadmium, which is important, if we use chemical this thing, then 0.52 milligram per kg is there in tomato. And if we use 80% and plus sludge, it is 0.43. Irradiated sludge, 0.46. So what we mean to say is that by use of this treated sludge with bio NPK, there is not much change in heavy metal concentration in the crop. Whether it is tomato, same way we tried wheat, there also we find there is insignificant change by use of the sludge. And then potato also we tried, and the same similar results were obtained. So that proved that use of this treated sludge is safe for using this kind of crop. In separate study we have done only treated sludge of the order of 1, 2.5, 5, 10 tons per hectare. What we are talking is only 1 ton, but we have tried up to 10 tons. And we found that as such, nothing happens, but in 10 ton per hectare yield was comparable to 5 ton. But in some crop, there was little more concentration of cadmium in the crop if we use 5 ton or 10 ton. But 1 ton per hectare is very safe. So no significant increase in heavy metal in the crop or soil. We have not considered organic toxins, but since we have reduced the use of sludge, then this, even if they are there, they will be much smaller than the requirement. IAE Tech Doc 2003, they have a full data on this movement of heavy metals to the crop. But there, none of them have used PGPB, but direct sludge they have used. The use of sludge quantity is much less than some people say our soil will be full of sludge if we keep using sludge, but the sludge quantity is much smaller than chemical fertilizer. So in general, it is not going to change the soil fertility or any other nature. So we can safely use sludge. So benefits of treated sludge is it provides organic carbon, soil conditioning, import substitute for fertilizer. If we are importing fertilizer, then reduction in 20% of fertilizer will be import substitute. Adverse effects are minimal, environment friendly, recycling of waste material, revenue loss to revenue generation to STP facilities. Initially, it is a big loss to sewage treatment plant to dispose this material, which is very expensive. In fact, 50% of sources are used for disposing. Now they can generate revenue from this. So biogold, a better way to recycling of a waste material. So I mean, this is what we would like to say. And then when radiation technology helps common man, atoms smile. So this was my second lecture, and thank you very much for your attention. I think I have completed in time my third lecture. If you want me to continue, I will continue. I hope internet has come or no? And the sound is not there. If the third one, if they want to come, they can. Otherwise, I will continue. Yeah. So should I continue or leave it? Because time is. Yeah.
Radiation technology for textile.
Yes. So we can take 2-3 questions after this, or maybe if somebody wants to ask on sludge hygienization, we can take 1 or 2 questions.
If you want, I can correct the screen.
Yeah, please. And the video sound was not coming, so maybe this also has one video. So I think Turkey should go for one such facility of sludge hygienization. At least Izmir, which is a smaller population, so they can make. And I am here for full 5 days, so if anybody has question, discussion, they can talk to me how exactly we can go about this project. Can I start?
Yes, you can.
It's not on the screen, but I can speak. Forward.
For that, you need to use it.
Okay. So I welcome you for my third presentation on effluent treatment, and this is also one of the biggest problem in our country and maybe in most of the countries, because everybody use clothes and other thing, and we are fond of colors, and this kind of problem is there in our country on large scale. Now, if you see textile dyeing industry which are present in India, they account for 14% of GDP and 27% of export earning. We are 1.4 billion people, so definitely our textile industry is huge to meet our requirement. So there are about 10,000 big garment manufacturers and 2,200 bleaching and dyeing industry in India. So these are some of the states like Kolhapur, Erode, Gujarat, Ludhiana, Jaipur. They are the major sector who are producing textiles. And this is how you can see the sewer water is coming out of and this colored. Actually, it should be colorless, but it is there. And we have this water is treated in effluent treatment plant. So you can see there are different stages like pH adjustment, then equalization tank, then primary treatment, then it goes to settling tank, then biological treatment, then effluents are discharged. Now if we have to put electron beam or gamma facility for effluent treatment, where exactly we have to put the facility? Now is a big question mark. We say effluent treatment. Effluent treatment, see the smaller units, they cannot afford accelerator or gamma facility. So what people do, there are cluster of industry, small scale industry, they join together and make a common effluent treatment plant. Mean they send their effluent to the common effluent and then collectively they treat. But then what happens, that common effluent treatment plant, the waste is a cocktail of many dyes, TDS is very high, COD is very high, salts are very high. So it's really a difficult mixture. So they mostly coagulate, then they generate sludge, then they do biological treatment, and then they meet requirement and discharge water. So even without electron beam or gamma radiation, they are meeting the requirement. But it is expensive process for them. They feel it is expensive, difficult to maintain, and smaller textile units cannot afford. So it is easier to dispose in sewer line. So they simply put in the sewer line and spoil the sewer. Now if we see the dyeing industry, you see there are number of dyes which are known as acid, basic, direct, disperse, metal complex, reactive dyes. Now if you see when they use reactive dyes, especially red, blue, green, then 10 to 50% is lost. I mean 50 to 90% is used in fixing on the cloth, rest is lost to water. Mean the water becomes color. So same way almost all dyes, some part is fixed to the cloth and rest is lost to the water, and this water need to be treated. And if you see the effluent, the values, you can see COD is 900 to 1000, BOD 400, pH 10 to 11, suspended solids 120 to 268, and sulfate, oil and grease, all are there. Now COD should be less than 250. I will talk about how this 250 is important. But actually, CODs are less than 2000, sometimes it is even 5000, but they are 900 and this thing. And BOD should be less than 30, pH 7 to 10, suspended solid, dissolved solid, sulfate. I mean, there are fixed standards given by government that before discharging this kind of thing should be met. But if you see the real thing, they are far, far away than the discharge limits. And then in our country we have one this electron beam center where we are studying electron beam applications as well as manufacturing of electron beam. We have technologies developed for 10 MeV, 10 kilowatt, then cargo scanner, then 1 MeV 100 kilowatt accelerator, and then medical linac. So all these technologies we have already developed, and we are now starting to sell this kind of accelerators to local companies. Now this is 1 MeV 100 kilowatt DC accelerator in our facility, which we used for water treatment, textile industry, and our experiment was at the order of 10,000 liter each experiment. So because small scale quantity doesn't give any much information. This is how, this is our 10,000 liter tank in which we fill the water, and then we irradiate under the scan horn. This is 1 MeV 100 kilowatt scan horn. Now this is some before trial we did some studies. This I will not go in details, and you can see these dyes, they are highly, their molecules are very big. There are chromophore which causes color, then there are groups which are responsible for solubility, then reactive groups which fix to the this thing cloth, and you can see it's such a big molecule. And when we irradiate this kind of molecules, what will happen? It will break from here, it will break from here, some color may go. In fact, a different color may also form because of reorganization of the molecule. See, the problem is when we are trying to reduce COD, chemical oxygen demand, the carbon remains in the solution. So COD doesn't go down very much. It requires very high dose to reduce COD to significant level, and that is where the economics comes into the picture. So let's see example how we use 120 ppm. This is how the water was flowing under the scan horn, and you can see this is only water and the dye with 0.75, 1.5, 3.75 kilograde. The color has gone. But that does not mean that COD has come down, because after degradation the carbon molecules remain in the solution. So this is not the final solution we want. We have to meet all the targets. COD should be less, BOD should be less, then pH, TDS, suspended particle, all should reduce. Then only we can use this radiation technology. But radiation technology alone cannot bring the result which we require. So we have to combine it with other solutions. So we have seen this, we have used two dyes, reactive red, they are 147 ppm and 191 ppm. We can see how the BOD is increasing, BOD and COD ratio is increasing. You can see in the red, the COD is first increasing and then started decreasing at 10 kilogray. So this is how the chemistry works out by using this kind of this thing. But you see the toxicity is gone. This is all the water we have used, that different kilogray which I have shown you. This is the control one, and we have put some seeds to observe their germination. Now if you see, except in unirradiated, all irradiated show the germination of seed. That means the toxicity, initial toxicity of the dye has gone. This is again a synthetic. We have tried to see how exactly electron beam and gamma radiation, they are comparable. In fact, gamma gives better degradation, electron gives better degradation initially. And as I told you, the common effluent treatment plant may not work alone. So we have taken a wash cycle. I mean, we first dye the cloth and then wash it with water. 1 kilogram of denim cloth, jeans, requires 200 liters of water to clean it. So when with this 200 liter of water is coming, it contains dye, blue dye, red dye, green dye, depending upon the color. But that color is less in concentration, and 80% of the water used in textile industry comes from wash cycle, when we are washing the cloth after coloration. So you can see here also TDS is 4200, COD is 299, which is quite less. In CTP, because the limit is less than 250, is more or less clean effluent. And OD is also 0.240. And we can see as we increase the dose, the OD, I mean, which is reflecting the color, is also decreasing. But in radiation case, it did not decrease to significant difference. It went to 0.165. So what we did, the ozone generated during irradiation, we pumped that ozone into the effluent, and that color immediately went down. So it is beneficial to use ozone generated in electron beam accelerator along with the radiation dose to reduce the dye. But according to me, these are very clean effluent. Now this is the common effluent treatment plant effluent, and you can see even after giving 100 kilogray, there is hardly any change. In fact, the color has changed. So this doesn't work on thick common effluent treatment plant. It can only work on lean solution, which have less. Now, for example, 2022, the China experiment, which is results are published in Radiation Physics and Chemistry, they have COD initially 500 to 700, then they did chemical and biological process, brought it to 180 to 280. See, the limit is 250, so they have already cleaned the solution, and then giving 1 kilogray to reduce COD to 15 to 20. So that shows that this kind of process works on lean effluents, where lowered COD, TSS, TDS, but it doesn't work on real effluent which industry is facing. So we have to have a separate stream for wash cycle and then treat it, so probably that may work. So exactly we have to study where exactly this kind of system have to be put in the industry. So we cannot just say take accelerator and treat effluent. Each case has to be studied before we can put up these kind of facilities. Now we also tried tannery effluent with leather products. There you see nothing happens to the COD. COD more, see, these are the standard initial values of COD is 2000 to 4000, and after treatment there is hardly any change in COD. But interestingly, we found that chromium get reduced by 95%. The chromium, leather industry chromium is a big problem, and that reduced to 95%. Basically radiation cannot do anything to metal, but this insoluble form is getting converted into insoluble form and precipitates. So we are able to remove chromium from leather industry effluent. But we could not use because COD, BOD are not changing and they are far beyond. But this is a very good observation that it can treat chromium. So it is, see, leather treatment shows that it is important to know what are the contributors for COD in the effluent. E-beam treatment may not be effective at all in certain cases. So, as I told, you have to study each and every case. It's not a, ticket for all effluent solution. You have to study and then find out the best way for treating this thing. But one thing is definitely sure, that lean solution can be treated with radiation technology, whether electron or gamma. But then question comes, lean solution can be treated by other technologies also. You simply pass ozone, that will take care of it. So electron beam is not required in that, even in that case. So where it is required, industry people will see how economics work for them, whether to put up an accelerator or gamma facility or simply buy ozone and just pass ozone through it. So that all is dependent factors. So what we observed that instead of using electron beam technology in one place, why not to divide dose? Let's say we have to give 10 kg. So we give 5 kg before biological treatment. So what we have observed that biological treatment efficiency increases by 10 to 15% because the molecules are broken down by radiation. And then later on use it again rest of 5 the kg after treatment in the final stage. So the division of dose works very well to treat this kind of solution, which may be even COD can be 500, but even then we can treat. But only one dose is not able to treat thicker solutions, only lean solution we can prove. So before biological treatment and after biological treatment we divide the dose and give. So radiation dose, because of the radiation dose division, we get lower sludge generation, higher discoloration, higher COD reduction, lower load on RO system for reuse. Same accelerator to be used after different treatment cycle. So that's how we can design our own way to treat effluent. So finally, electron beam or gamma facilities are mostly electron beam will be useful for wastewater treatment. For wash cycle it is very good. So this effluent need to be combined with other methods like chemical and biological treatment for treating common effluent treatment plant effluents. I mean directly we cannot treat. We have to treat it beforehand and then do it. So we have met industry people, we have gone to industry, discussed with them what are the issues, whether they would like to put up. See, the large investment required and industry is hesitant to adopt as a cost treatment per kiloliter is much higher than conventional method. They are using conventional method to treat and they are able to meet the discharge limits. So the high initial investment cost they don't want to put. So as such, industry is under pressure due to zero discharge policy of government and scarce water. So they are looking for better and economic solution. So if we can show them, yes, this technology helps you to save money and solve your problem, they are ready to invest money. There is no this thing. But we have to prove that they can use it. See, now for example, common effluent treatment facility, their input is 300 mld. Now with the kind of accelerator or for facilities we have, we can treat 2 mld, 5 mld, maximum 10 to 20 mld. So that doesn't solve their problem. Again they have to look forward to other methods. So these are some of the questions, and that is why these technologies are not coming up, because we are not able to demonstrate that these technologies can help to save money and solve their problems. So this is the big bottleneck, that how to go about it. So one way is to directly use radiation technology. Another way is indirect use. Indirect use means we are producing grafted material which can pull out dyes from the water. And these systems are much cheaper, much affordable, and they do all the job of electron beam. So why not go for this kind of system? Now this dye system, grafted system, they also remove dye from lean effluent, removes arsenic from groundwater, removes chromium from groundwater. They are antibacterial, low capital investment cost. Technology, we have transferred this technology to few companies, and in $3,000 US you get the machine. And where is $3,000 and where is millions of dollars? So industry would like to go for such kind of system which can be accepted by most of the people. So that's how we found that this is taking place much faster than our radiation technology itself. Although the product is made by electron beam grafting. So this is a monomer which we graft on cotton cellulose. I think even people here can try in their lab. simply purchase this monomer, take cotton, wash it, clean it, put together and give some 3 kg radiation dose, you get the material. Wash it and then you can use it. So you can produce positively charged grafted cotton as well as negatively charged grafted cotton. So you can remove opposite charge dyes. See, dyes are either positive charge or negative charge. So you can remove this kind of from effluent. And from this cotton we can make cartridges like this. So each cartridge is of about 5 kg. So you can put these cartridges and we can make a small machine like this, which is very simple. There are steel cylinders, there are cartridges inside it, and then there is an inlet of effluent and outlet of effluent, which is a similar to water filter, and there is a pump. So we can 20,000 liter we can treat every day with 200 milligram with one cartridge only. The machine, and this machine has 4 cartridges. So each we can make 20,000 to 25,000 liter effluent by this machine. So this becomes very cheap and affordable solution. So that's how these machines are getting popular. We have already given 10 machines to industry, and now technology is given, so they will sell it. Now if we make it using plastic, this machine can become of the order of $1,000. So this becomes really useful. Now you can see the high COD, BOD colored water, and after treatment this is the case. I think there is a movie you can play on this. So we not only to look for radiation technology, we can use product made by radiation technology. And this is just our mobile phone movie which we made during one of the presentation. The sound is not coming again. So this can treat about 2,000 liter per hour. So in a day, 20 hours, if we treat, we can 40,000 liter we can treat. See, you can see one side this type of water is going in and this type of water is coming out. It's just for demonstration we have put, but even 1,000 liter we can put it. So we showed it to different people, concerned people, that how this Ramamurthy, our former director at IAEA, and these are municipal commissioners, we invited all people to see how it can be done. And we are further improving this technology. Now this, we installed this in industry where they are cleaning and washing water is fed to this machine, and again clean water is being used to wash this cloth. So I mean, you wash, clean it, again wash, and then again clean it. So 40,000, see, you can see how this is again reused water. I don't know sound, what has happened.
Sound next to it is room.
Okay. You can escape this. So this, our chairman was there during demonstration of this small machine in the industry. And next is chromium. See, chromium is also a big problem where leather industry is there. The same column we can use for removing chromium. Now you can see the treated water and the original water. And after this can treat even 50,000 to 100,000 liter of chromium contaminated water. And recycling is very easy. Just pass saline through the column, whole chromium is out. Chromium is in the form of chromate. So we have a grafted positively charged, so it picks up chromate. Same way arsenate. Arsenic is also removed from this using the same column. And we have supplied this system to Bangladesh. at gratis to use this machine to remove arsenic from their groundwater, and they can use it. In India also arsenic problem is there, so we are trying to give away. These are cheap machines, so people can use it. And we are making home system also, water filter. So, but some issues are also there. It is a multi-step. See, for industry they have to see. It is a multi-step process. Known availability of radiation source, choking of cartridges, usability and disposable. So we have found out, we are redesigning cartridges. Then we use disc filter. I mean, these are kind of filters which remove TSS and solid particles. Then whatever cloth is there after use, we can bleach it and make bags. So they are reusable. Coagulation and flocculation of waste water before use, we can use on high COD effluent also. This kind of machine is usable. So this is my team. When I was there, they were all awarded for developing this technology, and which is of real use to industry. And thank you very much for your attention. Actually, this lecture, one lecture, I generally give for 1.5 hours. So, in real sense, I would have got at least 3 hours, but I have tried to finish in time. I hope now it is 4 o'clock, so it's okay. So, any question we can take, 1 or 2 questions, if the time permits.
Coffee break.
Okay. Thank you so much for your attention. Sure, sure.
Thank you Mr. Voshne. Program kaydı için kahve arasında 10 dakika veriyoruz. 10 dakika sonra Sayın Ergun sunumuna başlayacak. The program is shifted. Coffee break is only limited with 10 minutes. Please, 10 minutes later we can continue. Argun'un müsilaj arıtımı ve bitki büyütme ajanına dönüştürülmesi başlıklı sunumu ile devam ediyoruz. Kendisini kürsüye davet ediyorum.
Sayın katılımcılar, herkese tekrar hoş geldiniz demek istiyorum. Zamanımız kısıtlı olduğu için biraz hızlı konuşacağım, kusura bakmayın. Bir önceki sunumda mikro kirleticiler hakkında konuşmuştuk. Şimdi tam zıt bir yöne devam ediyoruz. Bu sefer makro kirleticiler hakkında örnek vererek konuşmak istiyorum. Bugünkü sunumumuzdaki konumuz müsilaj. Türkiye'den katılımcılar gayet konuyu iyi biliyorlar aslında, yaşadığımız felaketi, ama yabancı yurt dışından gelen misafirlerimize kısa bir hatırlatma ve açıklama yapmak istiyorum. 2001 yılında Marmara Denizi'nde bir müsilaj felaketi yaşadık. Marmara Denizi kapalı bir deniz olup müsilajla ilgili bütün kıyı alanları bir örtü şeklinde tamamen kaplandı. Şekilde, resimde Marmara Denizi'nin yüzeyinin kaplayan müsilajın havadan görüntülerini görmektesiniz. Peki müsilaj nedir? Müsilaj jelatinimsi, polimerik ve organik bir maddedir ve birçok bitkiden ve bunun yanında bazı mikroorganizmalar tarafından üretilmektedir. Örneğin fitoplanktonlar, bakteriler ve mantarlar gibi. Müsilaj temel olarak aslına bakarsanız polisakkarit denilen büyük bir molekülden oluşur. Polisakkarit dediğimiz şey monosakkarit, yani basit şekerlerin bir araya gelerek polimerik bir yapı almasıyla oluşturduğu bir moleküldür. Bunun dışında aslına bakarsanız bildiğim kadarıyla polisakkaritler dışında glikoproteinler ve daha birçok organik molekül yapısında bulundurmakta, ama temeli polisakkarit olduğunu söyleyebiliriz müsilajın. Peki müsilaj neden oluyor? Genellikle deniz müsilajı fitoplankton adı verilen mikroskopik bir canlıların fazla çoğalmasından meydana geliyor. Plankton dediğimiz canlı aslında tek hücreli bir organizma. Bildiğim kadarıyla Yunanca bir kelimeden türemiş, planktos adı verilen bir kelimeden türemiş. Kendi kendine hareket edemeyen ama mercan gibi de sabit kalamayan, bulunduğu denizde veya su ortamında denizin suyun hareketiyle ancak hareket edebilen ve denizde bulunan birçok canlıya da besin kaynağı olan bir mikroorganizma. Peki neden bu kadar fazla üredi? Bu tamamen aslına bakarsanız yoğun endüstriyel ve nüfus artışından dolayı atık suların yeteri kadar arıtılmaması ve o şekilde deşarj edilmesi, aynı zamanda da küresel iklim değişikliği, yani havanın biraz ısınmasından kaynaklanıyor. Atık suların yeterince arıtılmaması ve denize aktarılmasıyla bu fitoplanktonların aslında besin kaynağı sağlıyoruz. Yani bunların beslenmesine neden oluyoruz. Dolayısıyla da üremesine ve çoğalmasına neden oluyoruz. Küresel iklim değişikliği, yani havanın ısınması demek ise sıcak ortamda üremelerinin artması demektir. Peki problem nedir? Neden böyle bir sorunla karşılaştık? Artması çevre açısından ne gibi bir problem yaratıyor? Az önce de söylediğim gibi deniz yüzeyini ve hatta deniz altını bir örtü şeklinde, battaniye şeklinde kaplamasına sebep oluyor. Bu da oksijen transferini, yani denizlerdeki canlılara oksijen gitmesini engelliyor. Dolayısıyla canlıların toplu ölümüne sebep oluyor. Aynı zamanda jelatinimsi polimer bir yapı olduğu için içerisinde bir takım patojen bakteriler ve virüslerin de anaerobik ortamda da üremesine sebep oluyor. Tabii ki bütün bu durumlar hem turizmi hem de balıkçılığı oldukça negatif yönde etkilemekte. Bu müsilaj sorunu başladıktan sonra Çevre ve Şehircilik Bakanlığı bir acil durum planı hemen devreye soktu ve ilk olarak hemen yüzey temizleme botları denizin yüzeyinde bulunan ve altında bulunan müsilajı hızlı bir şekilde temizledi, topladı ve bertaraf etti. Tam bu noktada bizim de aklımıza bir fikir geldi diyebiliriz. Bu müsilajın çevre yararına nasıl kullanılması ile ilgili çalışma arkadaşlarımla konuşurken acaba bunların ışınlandıktan sonra organik gübre olarak, yani besin olarak kullanılıp kullanılmayacağını araştırmaktı. Aynı zamanda ışınlama bu Çalıştay'ın başından beri anlatıldığı gibi zararlı bakterileri, organizmaları da öldürmekte. Dolayısıyla müsilajın içinde bulunan zararlı mikroorganizmalar da ışınlamayla ölecek ve müsilaj aynı zamanda parçalanarak bitkilerin besinleri daha rahat bir şekilde alabilmesini sağlayabilecekti. Tabii ki bu konuda tarım ve gıda grubu araştırmaları yapan gruptan da çok büyük destek aldık. Kendilerine çok teşekkür ediyorum. Çünkü bizim uzmanlık konumuz değildi bitki yetiştirme. Gördüğünüz gibi slaytta ışınlamadan önce ve farklı dozlarda ışınlandıktan sonraki müsilajın görüntüleri. Işınlama dozu arttıkça müsilajın o polimerik ve jelatimsi yapının kaybolduğunu, daha sulu bir forma dönüştüğünü görüyorsunuz. Işınlanmış müsilaj örneklerini belirli işlemlere tabi tutup sulamak için direkt olarak kullanmadık tabii ki. Gördüğünüz gibi ışınlanmış örneklerden 50 gram alıp 2 litre tap water, çeşme suyuyla karıştırarak aynı miktarda ekilmiş domates tohumlarını sulamakta kullandık. Tabii ki bu etkiyi olumlu veya olumsuz yönde değerlendirebilmemiz için bir de kontrol grubu oluşturmamız gerekiyordu. Kontrol grubunda yine aynı şekilde dikilmiş domates tohumlarını sadece çeşme suyuyla, yani müsilaj içermeyen suyla suladık. Bu tabloda deneyimize, çalışmamıza, araştırmamıza başladıktan sonra çeşitli tarihlerde bitkilerin büyümesini gözlemledik ve bunları fotoğrafladık. Gördüğünüz gibi ilk haftada, yani sulama başladıktan sonra ilk haftada filizlenme meydana geldi. Aslına bakarsanız kontrol grubunda filizlenme daha fazla olmaktaydı. Işınlanmış müsilajla sulanan tohumlara nazaran. İlk haftadan sonra baktığınızda ise müsilajla sulanan tohumların büyüdüğünü, yeşerdiğini, aynı zamanda kontrol grubunda da aynı etkilerin görüldüğünü görüyorsunuz. Ama bir ay sonra kontrol grubuyla, yani müsilajsız suyla sulanmış bitkilerde solmalar meydana geldi. Ama müsilajla, ışınlanmış müsilajla sulanan tohumlarda, bitkilerde ise canlılığın devam ettiğini görüyorsunuz. 9 Ağustos'taki fotoğraflara özellikle dikkatinizi çekmek istiyorum. Kontrol grubu tamamen solmuş durumda. Ancak özellikle 18 ve 23 kilogram ile ışınlanmış müsilajla sulanmış bitkilerin gayet net, sağlıklı bir biçimde olduğunu görmektesiniz. Tabii ki sırf gözlemle bir sonuca varılmıyor. Dediğim gibi ziraat mühendisi arkadaşlardan da yardım aldığımızı söylemiştim. Nasıl bir ölçümler yapılması gerektiği hakkında kendileri bize çok yardımcı oldu. Bu noktada fide uzunluğu, kök uzunluğu, dal sayısı, yaprak boyu, yaş ve kuru ağırlık gibi ölçümler yapıldı. Ölçümlerde de gördüğünüz gibi özellikle 18 kilogram ve 23 kilogram dozlarda ışınlanmış müsilajla sulanmış bitkilerin bütün bu saydığım parametrelerinin oldukça diğerleriyle karşılaştırıldığında iyi olduğunu görmektesiniz. Özellikle kontrol grubuyla fark olmaktadır. Büyüme bitkilerde ağırlık ve hacim artışı olarak tanımlanır. İşte bu noktada kuru ve yaş ağırlıkları da hesaba katılarak bir takım gözlemler ve deneyler yapıldı. Kuru ve yaş ağırlıklarında ise yine 23 ve 18 ve 23 kilogray dozlarda ışınlanmış müsilajla sulanmış bitkilerin en iyi performans gösterdiği görülmektedir. Yaş ağırlıktan kuru ağırlığı çıkarttığınızda bitkinin besin alımını yapabilirsiniz, değerlendirebilirsiniz. Bu durumda da yine 18 kilogray ve 23 kilogray dozlarda ışınlanmış müsilajla sulanmış bitkilerin oldukça besin aldığını ve dolayısıyla da canlılığını buradan kazandığını söyleyebiliriz. Birkaç önceki slaytta da söylemiştim. Gübre olarak kullanımı gayet başarılı olarak gözüküyor. Ancak müsilajların içinde zararlı mikroorganizmaların da olabileceğini, dolayısıyla sulama yaparken bu zararlı mikroorganizmaların da bitkiye zarar vermemesi gerektiğini söylemiştik ve ışınlamanın bunun için bir çözüm olacağını söylemiştik. Bunun kontrolü için ise mikroorganizmaların mikroorganizmaların oluşup oluşmadığına dair deneyler yapıldı ve bunun için de mikrobiyolojik ekimler gerçekleştirildi. Çok net sanıyorum ki görebiliyorsunuz. Kontrol grubunda, yani sadece çeşme suyuyla sulanmış suda bakteri gelişimi oluşurken ışınlanmış diğer gruplarda dozdan bağımsız olarak herhangi bir mikroorganizmanın gelişmediğini ekranda da görmektesiniz. Sayısal verilerimiz de tabloda yer almaktadır. Çok hızlı anlatacağımı söylemiştim. Kusura bakmayın vakit yetersizliğinden dolayı, ama özetle bu çalışmada aslında bir doğa felaketi olan müsilajın nasıl yararlı bir kullanım alanına dönüştürülebildiğini ışınlama teknolojisiyle görmüş olduk. Tabii ki bu çalışmalar daha da ilerletilecek, çünkü hep söylüyoruz, laboratuvar çalışmaları daha sonra kesinlikle alan, saha ve pilot çalışmalarına dönmeli. Bu tohumların tarlada ekilip daha sonra tekrardan bütün değerleri açısından değerlendirilmesi gerekiyor. Bütün parametrelerin değerlendirilmesi gerekiyor. Dinlediğiniz için teşekkür ederim. Bu kadar.
Sayın Ergun'a sunumu ve hızı için teşekkür ederiz. The next presentation comes from Dr. Sanil Sapharval, Economic Evaluation of Radiation Technology for Environmental Applications. Dr. Sapharval, can you hear me?
I can hear you, yes.
Okay.
Can you hear me?
Yes, I can hear you. You can share your presentation.
Yeah,
I
just
will
give me a
wait.
moment, please.
Okay.
Yes. Can you see the screen now?
Okay. Yes.
Just a minute, yeah, full screen now.
Yes. Thank
Okay.
you. The floor is yours.
Fine, thank you so very much. And a very good evening now to all of you. Probably you are refreshed after the coffee break. My lecture now is going to be on economic aspects of radiation technology for environmental remediation. Just a brief recap. We learned yesterday in the first lecture, it's not learned actually, I informed you, that radiation technology for pollution treatment has been demonstrated very effectively for flue gas purification, wastewater treatment, and sludge hygienation. But no presentation or no meeting is complete unless somebody asks, okay, at what cost? You already have learned from many speakers what are the cost estimates that they have for their technologies. Now, being at IAEA for many, many years, I will try to give you an overall view of what I had learned from various experts who have been working in this field. As Dr. Pillai in the morning told about a meeting that we had held probably about 6-7 years ago, where we have assembled everybody related to different technologies to discuss about these aspects. Many of the information that I have will be from that meeting. And the idea I will have, as I said earlier, is a very broad overview of the economic aspects of the technology. And now the very first thing that when I talk about it and when you discuss it at a very large scale with, let's say, UNDP or UNEP, these kind of things, you realize that economics is not the same as the financial cost. Economics is very different as compared to the financial cost of the project. A project is economically viable if the economic benefit of the project exceeds its economic cost. And when it is analyzed for the society as a whole, the economic cost of the project are not the same as its financial cost. External and the environmental impact should also be considered. This is there in the very recent report of the World Bank. You could assess it on the internet. It is published in 2022 in the month of June. When I look at that, let's look at the impact of the technologies that we have discussed. Sewage sludge. Globally, unclean water poses significant risk of diarrhea, opportunistic infections, and malnutrition, and it accounts for 1.7 million deaths annually. And 90% of this is in developing countries, and almost half are children. Now, these deaths are primarily due to ingestion of fecal pathogens from humans or animals. And obviously, they all come from the sewage sludge. So if you can see where there is a question of 1.7 million deaths and half of them for the children, what costs are we going to put to the technology? How do we evaluate? If I will take the next one, this is related to the dye waste water. Now, as has been discussed earlier also, the average dye factory uses about 1.7 million liters of water a day, and about 200 billion liters of effluents are produced per year. 72 toxic chemicals can be released into water in the dyeing process, including heavy metals. And 30 of these chemicals cannot be removed once you have put it into the effluent. And this again is published in the year 2012. On the side, you can see which are the countries which are doing or working on these kind of things. It is not the whole world anymore. You could see that China, India, and other Asia accounts for almost 75% of the dye production or the textile dye industry in the world today. So the focus is in these countries. This has become a very, very huge problem as compared to many of the developed countries. Coming to now look at the impact of the air pollution. Now, these are the figures of the economic cost of air pollution from fossil fuels as a percentage of GDP of various countries. Now, China loses about 6.6%, which is close to $1 trillion a year due to air pollution. I remember one of the instances when I had visited Shanghai, and after I came back after 1 month of that, the whole Shanghai airport as well as the city was closed for almost 10 days. No economic activity, no people coming here and there. You could see the cost at the air pollution, and much of it comes again, as he said, is fossil fuel burning, which produces SO2, NOx, and other things, along with the particulate matter. In the country where I live in, India, 5.4% of the GDP. In the United States, almost 600 billion are lost because of the air pollution activities, which accounts for 3% of the GDP of this. So once you look at these figures, you will realize that any small contribution you can do with your technology to overcome these is worth the money that is being put to overcome these. So as far as the economic aspects are concerned, I am very clear at least that none of the activities can, if you talk at a large institution like UNDP or UNP, UNEP, they always accepted these and said, yes, these are very important technologies, and that was my understanding when I was at the IAEA. I also heard a very interesting talk from Professor Muhammad Al-Shekli regarding the PCB study. And I remember from there, Andra Sagatova and Professor Fuluk have been working in many years. Again, TBC in 50, 60, 70 is such a deadly chemical. The production stopped in 1970. Are you able to hear me? Hello? Are you able to hear me?
Yes, we can hear you, but we can't see your presentation.
You can see the presentation? No.
We can't see your presentation.
Yeah, but I can see it on my desktop. Yeah. The video is on from my side. I can see.
Your network, I think, is closed, but maybe you can restart.
Just a moment. Let me see if I can.
Okay, we are waiting.
Can you see it now?
No, not yet.
You have my presentation with you? The PDF?
Biz açabilir miyiz? We are asking.
Yeah, I have sent it earlier.
Please wait. Maybe you can share again the presentation.
Okay.
If there's a problem, our colleagues try for you.
Just a moment. Let me change the location and then see whether I can still do it.
Okay. Şu an bomboşta mı? Evet.
No?
Hi, Sunil. Actually, your connection speed a little bit low. That's why Zoom closed. But could you try to reshare? or if we cannot manage, we can move from here, because we have your we have your presentations. You said.
Okay, I think that you can share and I can speak on from the transparency.
First,
Yeah.
try you try from your side. If we cannot manage, we can share from here, and I change. Sunil?
Yeah.
Okay, I think it's better to move the slides from here.
Yeah.
Okay. So, what was? Just say forward or backward.
You are able to see now? No.
Do you see?
You see?
Yes, I. Okay, go on.
Okay. Yeah. So you are able to see me now?
Yeah, I will follow from here. So okay, just go on.
Okay. So I was discussing about the PCB's problem with Slovakia. As you can see in this factory over there, from 1960 to 1984, they produced about 20,000 metric tons of PCB, and about 2,000 metric ton is still in the sediments of the river there. And it is one of the, not one of the most, it is the most polluted area in the Europe, and the river body almost 60 to 70 kilometers from there is no fishing allowed. The fish, as again Dr. Mohammed had explained, is able to digest the PCBs very effectively. So there is nothing of that kind possible, and that kind of economic loss you can have, if you have not treated your effluents properly. So these cases will show you that whatever we do, if you will look at very closely, economic cost can be huge. And we have to look at the economic cost of the process and not the financial one when you look at from a very, very upward position. Now, let me now speak about the financial aspect, which is about putting up the facility and how we convert, how we treat the environmental pollutants vis-a-vis conventional methods. These are the two industrial sources we talked about yesterday. In the chat, I had some questions asking about, whether it is later safer to dispose of the electron beam accelerator machine or the gamma radiation. So let me clarify once again, although Dr. Kamileski had said very clearly that nothing becomes radioactive with the kind of energy that we use. In the gamma radiation with cobalt-60, or when we use electron beam accelerator up to 10 MeV of energy, which are the two main sources for radiation processing, whether for industry or for the environmental application. So that should become very clear to all of you, that there are, whatever cobalt-60 is left is taken away by the supplier in the sealed lead sources. Nothing remains at your facility once the work is done. But work in the done means when the factory is to be closed down permanently. And with the electron beam, it can even be relocated to another location without any issues. These are some important definitions which most of the radiation technologists already know, but for those who are not radiation technologists in the audience, electron accelerators we define by kilowatts, that is energy of the beam multiplied by current. Gamma radiation we say by Curie or by Becquerel, whatever unit you wish to use. And most of the processes that you have heard in last 2 days, you say a dose which is in gray. That is the amount of radiation by an object or a person, and it reflects the amount of energy that radioactive source deposits in the material. And 1 gray is equal to 1 joule per kilogram. So as a thumb rule, generally higher absorbed dose means higher cost of the process under similar conditions of process operation. So having learned these, there are some facts which we should be very clear about. Ionizing radiation, either from gamma or from electrons, is an expensive form of energy as compared to energy, let's say, from heat. However, it is much more effective in generating free radicals as compared to other forms of energy. For example, what can you do with 1 kilowatt of thermal energy? Maybe toast 5 or 6 breads. Whereas with 1 kilowatt of radiation power, you can treat almost 8 to 9 tons of onions per hour. So that's the kind of difference you have when you use. It is so much more effective. Thirdly, radiation-based processes will be acceptable if they offer technical and economic advantages over other processes. Otherwise, it is very difficult to put them through. So a quick recap again. We see about flue gas purification. The radiation dose generally is about 10 kilogray. Now that you know what the gray is. For wastewater treatment, for example, in the dye, it was 1 to 2 kilogray. And for sludge hybridization, the dose varies from 3 to 10 kilogray. Now, coming to the cost of the power of the radiation power that we generate, let's first talk about from the electron beam accelerator. You see the cost of the power from the accelerator depends upon many factors. And one of them is how much is the power of the accelerator. As a thumb rule, the more power you can generate with the accelerator, although the machine will be expensive, but per unit cost is going to decrease. For example, if you look at this beam power varying from 20 kilowatt to up to about 1 megawatt, which Dr. Pillai said in the morning, about 1 megawatt power availability of the accelerators. You look at total cost of the machine varies from about 0.6 million US dollar, goes up to about 2.2 million US dollars. But when you will look at the per unit cost, that is per watt, if you convert the cost, it comes down from $30 per watt to about $2 per watt. So you can see that higher power accelerators are going to give you economic advantages. The only caveat is higher power must be utilized fully. That means you should have extremely high throughputs. Then you will be able to do these things very effectively. Now, coming to the cobalt 60. Cobalt 60 per Curie cost at present in the international level is about $3 a Curie. Plus, of course, you have transportation costs. So as Lalit explained in his presentation, that any plant that you make more than, let's say, 500,000 Curie, the cost of cobalt 60 is going to be extremely high. Again, if you will see that at about 500,000 Curie, it will reach 1.5 million US dollars, which is equivalent of roughly 200 kilowatt of accelerator, which is extremely powerful machine. So besides, of course, you having the facility, electron beam, you also have to have a shielding around that and a conveyor system. And both of them are going to cost you money. So the total cost, if you will see, will be the machine or cobalt 60 plus shielding plus conveyor. And if you look at this economics, the tentative cost of treatment with electron accelerator, for example, for the liquid sludge, the cost is about $1.24 per meter cube. And if you are able to take it to 18% solid, that means you centrifuge the sludge and make it a more, of course, it's very clear that the more sludge you have, the better is going to be your cost effectiveness. It can be brought to about 2.6. And if you will convert these values into dry sludge, then you will see there is a huge cost difference in the two values. Because this factor will get multiplied by 1.24 multiplied by almost 30, whereas 2.6 is going to be multiplied only by 5. So there is a huge amount of benefit if you are able to make electron beam accelerator treatment with 18% solid content. Vadodara model is the one, as I told you earlier, because I have worked with that plant for many years. We had at that time developed a model which was at that time propagated to various state governments and municipal corporations. The plant capacity I explained yesterday was 110 meter cube, which was for about 300,000 population. And if one had to design a facility for 1 million population, at that time, our cost estimates were a capital investment of about 300,000 US dollars for the shielding as well as for the pumping 1800 kilocurie cobalt 60. Again, Lalit had explained to you that it will cost you about US dollar 1.8 million, even though India produces its own cobalt 60. And at that time, when we had done this calculation, they were offering us at $1 a curie. And now it is $3 a curie. And if I will do the total calculation at that time, it was about 85.2 tons per US dollars per ton. Again, it was explained by Lalit had explained to you, this cost is high. As compared to this, the values that I showed you with the electron beam accelerator were almost 1/4 of these values. When we talk about the cost, as I explained you, the irradiation plant, Baroda plant, is put after the anaerobic digester and then going into the drawing beds. The later on model that is now being said is that you put it after the irradiation beds, after the drawing beds. In this case, one is that the dry sludge is going to take more dose as compared to the liquid sludge. And second is the drying has to be by the sunlight. I am not sure how under the different weather conditions of whether Europe or where there is a huge rainfall, when the drying takes place almost over 15 to 30 days, how that can be accomplished. So to me, that will always remain a challenge. And third thing is, if I dry it first and then irradiate, the issue is that whatever contamination I have to do in the environment, I have already done. For 15 days to 1 month, I have already put it into the open. So whatever contamination has to be done in the atmosphere, I have already done so. So these are the issues which I had when I was offered this dry sludge idea. I persisted it with the liquid idea and with electron beam accelerator of high power. Ultimately, anyway, one has to go to electron beam because cobalt 60 will never be able to meet these requirements of a large country. These was, as I said, I have already shown you that this was inoculated. I'm sorry for the dry throat. We get increased crop, which is a direct benefit. We get soil improvement, which is again very useful, reduce health risk. Again, many of these things Lalit has said, which we also were able to demonstrate with the Baroda plant. And we at that time have done about 700 tons of the material for this kind of testing. Again, you can see that large scale things. The issue of heavy metal again has been discussed earlier. The sludge is almost the same. There were no issues with the heavy metal in the domestic sewage sludge that we had. It could very easily meet the EPA standards without any issues. This is the slide which probably Professor Pillai has shown in the morning. When you compare cost per dry ton in US dollars for the different techniques, again you can see that incineration, thermal treatment, all of them are expensive propositions. They are not easy to carry out. And electron beam at its calculated guesstimate could be between 100 to 250 dry ton, which is much higher than what Bumsu has calculated earlier with the electron beam accelerator, which I had shown you earlier. Again, there is a misconception probably among many of the people that the sludge is not being used in the agriculture anywhere. If you look at it in details, and as we had discussed in the meeting in 2014, almost 50% of the sludge produced in the United States is already used in agriculture. It is already used in the forestry. Only thing is, after this treatment, it is not a class A solid, it is a class B solid. And class B solid has certain restrictions that you can put it either into the forestry or wherever you put for agriculture practices. Nobody is able to approach that area for 1 month of time. However, the conditions of class B biosolids are much less as compared to class A biosolids. What we have been proposing with electron beam or with gamma is that we convert it into a class A solid. But class B solid sludge itself world over, except for in Japan and in Germany, where they only do incineration. Everywhere else, sludge is being utilized in agriculture practices already. This is, again, I had shown you that the value addition is possible with the irradiated sludge because it becomes an excellent medium for generation of, rhizobium or some fungicides, or because there is no competition from any other bacteria or virus. These things can grow very nicely, and you can get extremely high values, a very high valued material, which can be sold at a premium in the market to meet your financial costs. This is again I have discussed yesterday. Now, this is another gem of idea from Bumsu Han when he was working at EB Tech before he joined IAEA, and he had presented this in our meeting. This was related to the textile dye wastewater treatment. His approach was simple. Analyze the existing process and calculate the present cost. The present cost that he calculated that time from the dye industry, again a common pool where every small dye manufacturer was putting his effluent. The cost was about 1.1 to 1.2 US dollar per meter cube of the wastewater. What he did was simple, that to work out the economics of electron beam, keep the target cost less than 1 US dollar, including biotreatment, which is the conventional process. So his target was that I wish to lower the value by 10 to 20% of the existing cost. And if I have to do that, the cost of radiation processing has to be less than 0.4 US dollar per meter cube. And that can be achieved only if the maximum allowable radiation dose of the process is 2 kilograms. That is how he fixed up the dose between 1 to 2 kilograms, and see with this dose what benefits can be derived for the industry. Whatever amount of chemicals could be reduced or whatever time of biological reduction could be reduced is the economic gain of the process, which is 10 to 20%. So to achieve this, find useful additives, find combination for lowering the doses with biosystem, with activated sludge, confirm this in the laboratory, make a pilot plant, go to the industrial scale, and finally commercialize. So he built the pilot plant. He showed with the help of IAEA as well as other KRE and Dev dye complex industrial scale design. But unfortunately, the commercial plants have been made in now China, or I will say, fortunately, commercial plants have now been made into the China, and I'm sure that in years ahead, this technology will be accepted. As you could heard also from Professor Hay and Suresh in the morning, 7 electron beam accelerators have been put at one facility of textile dye. That's the kind of work that is needed to be done and to be shown to the others in the industry. I have many times heard this document that accelerator is expensive. An accelerator today costs you something about, as I showed, $2 million to about $4 million or $5 million. A 3-bedroom house in Bombay, where I stay, a 3-bedroom house will cost you almost about 20 million US dollars. And we say that electron beam accelerator is expensive technology. It is just a mindset which people have to see that when they need it. Professor Kabileski has said very nicely in his yesterday lecture that once you make rules, people will then do it. Once you put the discharge limits in the manner which are to be followed and implemented, people will come and take the technology. But if those rules are relaxed, then of course nothing will happen. Comparison of electron beam accelerator also, which has been shown by Professor Kabileski. Wet flue gas, selective catalytic reduction. If you do them separately, they will cost about 120 and 110 is the investment cost. Let's take them together in the third one. That I do wet FDGD and SCR. The cost is about $230 million per kilowatt electrical, and annual operation cost is $7,600. Whereas with the electron beam EB FGT, he has shown that these values are much lower, 160 and 7350. The idea again was that we should be able to demonstrate the use of very extremely high powerful accelerators, whether 400 kilowatt or maybe 1 megawatt kind of accelerators running continuously for years together. Then we will be able to convince that, okay, we have the right technology for the treatment of this. But of course, for the smaller applications that he discussed, whether for the ships or for the ballast water, for those kind of accelerators, there are no issues. They are, routine in the industry today and can nicely be implemented. Now, this is a question, again, many people have asked. If this is so, why are there so few plants in the world? I would try to explain to you by this diagram. If you look on the y-axis is the significance of risk, and on the x-axis is the income of the population. If you look at, we have 3 different kind of nations: low income, in poverty, middle income, and then high income. If you look at different kind of risk, for example, engineering risk, for example, the risk of an aeroplane crash, it is almost the same whether you live in a low income country or you live in a high income country. If you analyze over the last 50 years, a similar number of plane crash must have occurred. So the engineering risk is defined by the blue line that you see at the bottom, right? This, which is more or less same for all the 3 countries, the type of countries. But if you look at the basic risk, lack of safe drinking water, sanitation, hygiene, in-air air pollution, vector-borne diseases, these are much higher in the low-income population countries, where the issues are now, as we have been discussing. These issues are not there in the rich countries, high-income or high society countries. But unfortunately, the technology and the resources are there with the high-income good people and not with the low-income good people. But look at the point where this is crossing, the intersection point. That is the middle-income population in transition. Countries which have got now good amount of income and are growing. Those are the countries, for example, large countries like China, you will see, their income has been growing per year, year after year. So they have now realized that environment is important and I must be able to put money into the environment. You will see India doing the same thing in the coming decades ahead. So, to my opinion, this is one of the reasons why there have been so few plants in the world so far. But hopefully now with the success stories we have from the large countries that are coming, this situation will change very soon, and we will see a lot more about radiation technology implementation to reduce the environmental risk conditions. Again today, I acknowledged yesterday and I acknowledge them again today, are the people who have put in tremendous efforts over the last few decades to bring these technologies to this level. My mentor and guide, Professor Kamuliski, a dear friend, Bum Suhan, Maria Helena Thampa, who was my predecessor in the IAEA, Professor Hay, with whom we worked so very closely to make sure that his dream of electron beam accelerator come true in China. Suresh Pillai, he has been a close friend, has worked together for many, many years, working together in India, giving lectures about use of electron beam accelerator in food irradiation that time, and now for, of course, the environmental applications. Professor Wang, who along with the Professor Hay is a good friend. Lalit has been a colleague for many, many years. I also wish to acknowledge Dr. Omar, who was our CRP participants, and all the IAEA staff members and participants who worked together with me in these meetings over the years. Thank you so very much for your kind attention. Thank you.
Thank you, Professor. We have time limited. Maybe the questions after in the chat box the participants write. Okay, thank you for your presentation and the contributions.
Fine, thank you so very much.
Okay, today's last presentation comes from Professor Dr. Mohammed El Sheikli, radiation-induced degradation of polymers for reuse in industrial applications. Professor Sheikli, can you hear me?
Yeah, I could hear you very well. Thank you so much. I'm just sharing my presentation.
Okay.
Can you see it?
Not now.
Can you see the presentation?
Not now.
No?
Okay. You can do the full screen, please.
Let me do it again.
No, we can see, but you can do the full screen.
Maybe
you cannot see
We
it?
can see the presentation, but not full screen. Maybe you can do the full screen again.
Can you see it again?
Yes,
No?
we can see it, but not full screen. You can do the full screen.
I'm sorry, you see it now?
We
Can you
see the
it?
presentation, no problem. We see the presentation, but
very good.
not full screen.
Okay,
You can do
very
the
good.
full
You see
screen.
it? Very good. Okay, so let me make it larger here.
Okay.
Okay, and let me see here. I guess, okay, so you see it very well now, right?
Okay, thank you. The stage is yours.
Okay, well, thank you so much. Good afternoon, everyone. Actually, here in Washington, D.C., it's still morning. And again, thank you very much for inviting me. I would like to really thank Dr. Omar Kantoglu for the invitation. Today, I'm going to talk about the radiation-induced degradation of polymers for reuse in industrial applications. And I like to as well to put as well my former PhD student, Lauralice Gonzalez Lopez. She graduated just a couple of weeks ago. And actually, most of the research here, the results came from her PhD thesis. It was the first PhD thesis to look about the recycling in determining this such a complicated issue here. One of the point here, just want to start talking about what the problem is. One of the most widely used types of thermosetting polymers are unsaturated polyester resin. Okay, they have a low cost and chemically inert, okay, mechanically tough, and good electric insulators. It is expected that the global unsaturated polyester resin market will grow from 9.6 billion to about probably 12.9 billion by 2026. The market is interesting, okay, and these polymer resins is just fantastic. They've been used for, especially used for the preventing corrosion. Literally, the corrosion in the shipyards and of course submarines. And think about how much submarines we have in this world, and you think about how many boats, ships, tankers. All these things, these polyester resin, they are outstandingly corrosion resistors. And therefore, it's been used a lot. Over the last, I would say, probably 50 years, it's been used a lot, especially this thermosetting unsaturated resin, to prevent corrosion in the marine industry and things. The question, of course, becomes what you're going to do with it. You have a lot of now marine shipyards. We have a lot of boats, huge ships, huge tankers, especially the oil tankers, which has been used here, is now out of the work because they are old. So the question, what you're going to do with this? This is the aromatic polyester resin. It's a huge problem. They are really, really good in preventing corrosion, extremely good. Okay, but the problem is now what you're going to do with it. I mean, obviously, so the becoming is for the Department of Energy, United States, is becoming a huge issue how to recycle these polyesters, and it's becoming very, very difficult one. By the way, as well, these polyester as well, they come out as well with different type of impurities. And then again, I'm going to repeat this statement here. We are dealing now with really dirt. They scrap things from the ships and they gave it to us. So, which is all that kind of, it has, let's call it a zoo of chemicals. So the objective of this work, actually, it is two things here. And this is very complicated. It is research focused partially on, they call it deconstruction of the West thermoset polyester. In other words, decompose the polyester itself, decompose it. And then after that, the second step will be the construction of it. In other words, you do the degradation, okay? You get a lot of things from it, usually a lot of monomers from it, okay? And then after that, you could do a construction, we make material from it. In other words, you could make material like a different type of oligomers, monomer to some extent. I mean, I'm using the word to some extent, but oligomers maybe it's a good way to say it though. These oligomers can be reconstructed again to make a different material. So this is the idea of the recycling here, which we are dealing with those polyester. Again, the construction first, and after that, followed by constructions. This is a slide to show you what I'm talking about here. This is if you look at the left side of the slide, you see the construction and the homolysis of these ester. This is the polyester here with the electron beam, and then here is the idea here to cleave these bonds, okay, to literally to induce scissions on the backbone of the chain or on the backbone of the resin itself, and followed by oxygen, and that to enhance the peroxidation. And then from the peroxidation, you will do so many things, and that could be what we call chain degradation reactions. Okay, that's really the thing. And then of course the step 3, okay, is going to be the more or less, it is the characterization and modeling of it. Okay, that's what we are working at the moment. And then after that, we will do what they call reconstruction. We use whatever we have here, monomers or oligomers we produce. After the deconstruction, we could construct it again to make a different type of materials. That's really what the idea here. So obviously now we are looking for literally the degradation and identification of these free radicals, followed by their reaction with oxygen, what they call it, to produce whatever you want to call it, peroxide radicals or peroxidation. And after that, you will have the construction to go to all those chain reactions. That's really the objective here. Maybe I should put it in this way. This is what we deal with. Look at this molecule. It's such a complicated molecule. This is the polyester resin. This is the structure of the esters here, and this is the phenyl resins. Okay, and then all the idea. You pick them up from different type of garbage, but literally here we are looking at the coming from the ship now, and then we have some reaction here to get them for the deconstruction, and then after that follow up by characterization, and of course after that we will look at the constructions. Challenges. The big issue with this one, this is a very cross-linked nature inherited in the thermoset structure. And this is the materials we are reaching, those polyester resin, they are very, very heavily already been cross-linked to be used to prevent corrosion or protect ships and shipyards and all those marine products from corrosion. So they are very, very cross-linked. So think about it now here. We are not dealing now with the simple molecules. We are dealing here with already cross-linked materials. Okay, that's number one. The other issue it is, of course, is the specific chemistry of these materials, because of the cross-linking density. They have a huge cross-linking density, and that's why they are very solid. They are very thermoset, and their hardness is extremely high. To, of course, again, to protect the shipyard and the ships from corrosion. Now, for the construction, okay. This is what we are looking for. The electron beam and of course and gamma rays. So the overall, actually, our work is now to look about how we can really new chemistries, recycling lithium polyester, involve electron beam treatment, and of course combined with the thermal construction. And then lastly, of course, the central question of this effort can be design energy efficient protocol for the crack recovery of the polymer derivatives from waste thermoset. That's really, after that, that's really big issue. That's what the issue it is. What is the issue of the economy behind it? How much we're going to spend to deconstruct and then construct, and how much gonna cost us? That's really the big issue. This is my lab is not really working on this issue. It's the other lab in the Department of Energy working on that one. We are just providing here the technical part. This is slide, I just want to remind you, though, radiation is obviously, as you know, as all of us know here, it is not a magic machine. Some polymers, this magic machine can, especially electron beam accelerator or the cobalt-60 radiation, the gamma rays. It is not really magic things. You put things in front of them, you get what you want. Absolutely not. It is a big issue regarding the structure of the material. So before we do one, I'm going to discuss this slide in some details on Thursday lectures, because that will really the effect of the radiation effects on polymer. But before I go there, I just want to remind you about the very important in this presentation, in this talk, about the glycosidic bonds, which you have them here in the polymethyl methacrylate, okay, and the cellulose derivatives. Okay, and of course, as well, you have it as well in the polyester. That's what we are looking for. We are really our target here on the glycosidic bond, not the quaternary atoms and not the fluorinated compound. Literally on the glycosidic bond, because the polyester, that's what it has. So our target is to literally attack that bond here. Obviously, as you know. If you irradiate, most likely people that will tell you, you're gonna cross-link things. Like, for example, if you take, say, polyethylene, you cross-link it. So it's not good. So this type of reaction, the cross-linking reaction. In other words, let me repeat what I said here. In these recycling, okay, this type of cross-linking reaction are not good for you. Actually, for example, in our case, it's already heavily cross-linked resin, polyester resin. So if we want to irradiate more, for example, and this reaction there, okay, that will make the things more even worse. All the idea is the other way around. The other way is that to make sure that the cross-link, we degrade or induce scissions on this backbone of the chain, taking into account as well the issue of the crystallinity. Thanks goodness, our resin. It is not that much crystal in it, okay, because of the types of the amorphous area in the polyester resins. The goal, of course, of our work is, again, it is not to cross-link like in the previous slide. Our goal, literally, it is to use degradation. and they take all those polymer chain, and of course you have polyester chain, okay, to degrade them. Again, degrade them through mainly attacking the glycosidic bonds. So this is, if you look at how difficult is one molecule here. This is one of the molecules from the marine has been used in the shipyard. Okay, it's outstanding materials. Okay, and it's been very heavily cross-linked, and it's to outstanding materials to prevent corrosion or to protect metals and stainless steel from corrosion. It is thermosetting. That's another issue here. It is and very, very, very good. If you look at this very, very carefully here, and I ask you people we've been asked how are we going to do the degradation, how we do the decisions here. Then you look at it very, very carefully. There are two things going to be. Some going to work for you for induce decisions or induce the degradation, but as well there is things in the molecules protected from that. Look at this. This is we have here they call it what they call the glycosidic bond. This is our job. So all the idea here to break these. You see, break these bonds here. The glycoside, the carbon, oxygen, carbon, oxygen, carbon, oxygen. They are very weak point, and on the top of that, they are really, they have not that much high resistance to radiation. But they're going to break very, very good for us, which is really, really good for us because that's what we want to do induce seizures. But we have as well phenyl groups here. Look at those, especially this phenyl group. This phenyl group can work to protect these molecules from degradation, because phenyl groups really take the electrons and these pi structures really take the molecules and protect the molecule. So the question is now how we have to make sure that we have to look at the free radicals, which is or the radiolytically produced free radicals which been produced after the induced decision on the backbone, taking of course into account you have as well double bond here. This could be work for you or could be against you. But so that's what the challenges which we have in this project. Before I go to the details about the radiation, current efforts of recycled thermoset resins, okay, at the moment, okay, there are the mechanical methods which involve grinding process of the material. They grind it very, very well, and they make it like a powder. And that powder can be, because you produce a lot of free radicals, and that can be decomposed, and you could really recycle it. But it's very expensive, and as well, it's not really competitive with radiation. Other method is actually the thermal method, which where the resin is decomposed by heating it up to about high temperature. The problem, of course, in this case as well, is very costly, and it takes time. It really takes time. The chemical method, of course, mostly concentrate on the polymerization of the resin. Okay, so in that case, the advantage which we have in the of ionizing radiation, okay, it is of course high rate of radical formation, okay, and of course high rate of degradation, and no need to initiators or additives like in the other cases, and can be done at room temperature. So that's really their most important things for the advantage of the using of the ionizing radiation, electron beam or cobalt, okay, versus those three methods, the mechanical, the thermal, the chemicals. So in our case, actually, especially in the people who they are doing the radiation using it for recycling, we have to demonstrate how the radiation has much more advantages than the mechanical and the thermal and the chemical one. That's really the most important things here. That's the advantage as I just put it here, as I just said it here. So the polyesters, okay, this is the physical and chemical character of the polyester, distinctive backbone, and then you see I'm going to put here the carbon oxygen, that's the glycosidic bonds here, which is make favored decisions. So that's really what we are here doing as well. And of course, the issue of the mechanism about the additive things, like for example, you have a double bond there, phenyl group, carbonyl groups, okay, in this region. I mean, the molecule is so complicated, okay. So in other words, it has a glycosidic bonds, it has a phenyl bonds, it has carbonyl group, it has double bonds. So all these things, those guys they have a different reaction to ionizing radiation. Okay, for example, as I said, phenyl group it has a very high resistance, like in the case of the polystyrene. Yeah, you cannot really degrade polystyrene with radiation. Absolutely not. It's going to go just cross-linking because of the phenyl groups. But in the esters, it's a very good one. It's a good one. It's like a very good candidate for the using of the ionizing radiation. So that's really very important. So, for example, as I said, in the presence of the carbon-oxygen carbon bond enhances decisions, and that good for us. It means enhances the degradation. The pi structure of the phenyl groups obviously gonna stop that from happening. So they have to balance between these two. Yeah. Considering to be taken into account for the polyesters, obviously, you have to have the issues. Oxygen, obviously, which we rely a lot on of the oxygen here, because all those free radicals, after it's been produced, we really want them to react with oxygen to produce the peroxidation reactions. The solvent issue, okay, and this is a big thing here. Yeah, think about it. As you have esters and thermoset ester, how you want to solvent to make sure that you enhance the effect of the radiation, and then if the radiation temperature. Okay, total dose and dose rate. Okay, now third rays, gamma radiolysis versus electron beam radiolysis, again as well, pulse radiation versus continuous radiation. All these things between oxygen, solvent, radiation temperature, total dose, dose rate, and pulse radiation, all this has a huge effects on the degree of the decision or the degree of the degradation and how that will be successful. Another complication is actually the one, just that goal to look at for the polyester resin used in industry to prevent corrosion. The issue, it is very complicated since these materials, I mean, it's not a pure materials. You're not going to go and take polyester resin from Sigma or think very pure. Absolutely not. These polyester, they have a lot of residual of vinyl monomers, many of them. So the question is now, yes, you're gonna go degrade them, but still those vinyl polymers probably they undergo polymerization as you degrade the polyester resin, but those impurities. Okay, it undergo polymerization reactions. So you have to be very, very careful with these things. That's the big complication facing us. And how now you prevent the polymerization of those phenyl polymers. The challenges of using solvent as well. Solvent are important to dissolve resin prior to radiation. However, solvent can compete actually for the radiation and act as a scavengers, like in the case, for example, when we use isopropanol. So selecting solvent are very crucial, but as well, radiolysis of water is very good, but water really doesn't really dissolve the solvents. But there's still, but in our case, actually, I could show you there, we mix the water with organic solvent, so that will enhance the solubility of the resin in that mixture, and then after that, we're radiating the water to get the hydroxyl radical. That's what I show you in this slide. This slide, you see this is the picture when you put the materials here. This is the action of water here. So if I take those resins, polyester resin, and dissolve them. Actually, I cannot dissolve them with water, of course, in the presence of water. And of course, I could have another co-organic solvent with them. I could produce, this is the wonderful stuff here. I have the hydroxyl radical. This is the one, the hydroxyl, the OH radicals. This is going to attack the resin or the glycosidic bond, hydrate electrons, H atoms, and those again has been producing a very high radiation yields. Okay, so that's what. So usually that's, and of course people, if they want to convert the electron to hydroxyl radical, you could use nitrous oxide to produce. So you could really double the yield of hydroxyl radicals to enhance the degradation of the polyesters. So the issue is now, in a way, if you look at it, though, I have a polymers here, and the code here is the aromatic degradation versus the cross-linking. So obviously, in our case, we're going to deal with the one for the inducing the sessions and things. That's really what the issue here. Here are the resins which we are dealing with at the moment. This is the marine use. This is the main component. This the dicyclopentadiene, and this resin here. It has a lot of look about maleic anhydride, phthalic anhydride, glycol, a small amount of vinyl monomers, methyl methacrylate vinyl. You see all these monomers in it with the radiation undergo really polymerization. So you have to stop this one. Another one, well, you have to degrade this one, and use radiation to degrade this one, but to stop the polymerization of this one. The same thing with this one, with this resin. Okay, and then we have another resin. So. And that's why. So we were dealing with 4 resins being used really to protect corrosion in the marine, especially in the U.S. marine, and as well. But those marines. So what we did, they gave us these. In our lab, we received those literally dirt. They scrap it from the ship. The ship already old. Okay, it's not under this service, but obviously they have to scrap them to take these for throw them somewhere in the landfill or. But now they said, okay, we have to do the recycling. So we are dealing with those 4 compounds. Still, we are working on them. We have a paper. I'll show it to you later on. The technique which been used, of course, here we use the dry. In other words, this resin. It's not been just a dry resin, okay, like neat. And then, of course, in the water, okay, in the presence of water, that's, again, it's not dissolved in water. It is just, we put it in water to take the hydroxyl radicals from water and get it to the resin. So you really attack the surface and a little bit inside. And as well, we have the water DMSO, dimethyl sulfoxide mixtures, okay, which is really good here because this is we could really dissolve the solvent. Dissolve the resin, okay, with this mixture, and as well we have isopropanol materials, and we use the irradiation here. We use it. This is type of the radiation we use, of course, electron beam and cobalt 60. This is the electron beam accelerator which we used, and this is the samples here. You could see it though, well, they're coming from the radiation. Obviously, we characterize it, and in this really presentation, mainly, and I'm presenting this result of the electron paramagnetic resonance, EPR, and probably the old guys like me, we used to call it ESR, electron spin resonance, but now they call it EPR, electron paramagnetic resonance, and we use as well the dynamic mechanical analyzer for looking at the changing in the glass transition temperature, because that's a very, very important one. And then as well the swelling, we use the thermal mechanical analyzer. Well, so this is today results I'm presenting here in this work regarding with these things. This is a paper we just published using the gamma on the mechanism of the steady state gamma radiolysis induced scissions and of the phenyl polyester base. And you could read it. It actually we just published in the Frontiers in Chemistry. And you could see a lot of things regarding the work which I'm presenting. The second paper has already been submitted to, and we are waiting for this to be. So this is here the EPR work here. This is the rate of the resin in the absence of the solvent and in water, and you could see it here. This is the resin. We took it just directly, okay, and we use the EPR, and you could see here the EPR results here. The EPR spectrum, you could see those hyperfine, and hyperfine been designated as the alkoxyl radicals. You see it here, and the other free radical here, which is really very, very important. It means we manage and successfully, let's put it this way, to cut the glycosidic bond. And that's really the idea. The objective is to cut it though. So the best way was obviously to use electron paramagnetic resonance to look at this one. As well in the presence of water, as well you could see it here react with the carbonyl and phenyl groups, and of course produce as well the alkoxyl radicals. So in both cases, in the absence of the solvent and in the presence of water, we managed to degrade and induce seizures on these resins. The same thing here with the IPA, with the isopropanol. Okay, the idea with the isopropanol is very interesting. Isopropanol really scavenge the radiation from you, but it produces electrons. So the other way, you use it to produce electrons, and the electron attack the resin, and then to produce those again alkoxyl radicals. And the same thing as well with the water DMSO. This is one of the successful story here with the DMSO. With the DMSO, with the dimethyl sulfoxide and water, we produce two things as well. The reaction of the, you could see as well the methyl group from the sulfoxide, okay, attack and produce as well type of the decisions here. What the important things is as well the stability of the alkoxyl radicals which being produced, and these we're trying to react them with the this is very difficult to react with oxygen, but this is react with oxygen. Okay, this is a strong oxidizing species, do not react with oxygen, but they could really abstract H atoms from the neighboring molecule to produce decisions as well. So kind of a little bit is very interesting radiation chemistry we are dealing with here. One of the issue it is here to when you produce those free radicals, okay, in the presence of oxygen, that's the role of the oxygen here. That's I mentioned it though. It's clearly that will produce what they call it peroxyl radicals, and the oxygen reacts with those radicals very, very fast. So it's fantastic really to look at these, to have this reaction to produce the peroxyl radicals. And those peroxyl radicals react sometimes with themselves to produce what they call it tetroxide. This is the action of the tetroxide here. You see how difficult it is. It's not really so. This is the formation of the tetroxide, and then the tetroxide. It is very unstable compound that will decompose, and this is part of the decomposition of the tetroxide here, which is we published this mechanism here, whereby you could see the from the polyester with the water molecules, and this is what they call it in the peroxyl radical degradation. They call it Bennett type of mechanism, where you could really see these type of things, and then the free radical will be decomposed, and much the decomposition, of course, that's what we are looking for in this case. We are looking for the decomposition and produce more and more. This is, you could see here, there's two things here. This is how the H2O attack the tetroxide here, okay, and that will enhance the decisions. Another issue here, this is the tetroxide here. This is the tetroxide that you can see the oxygen, 4 oxygen has, okay, and this is from one molecule, it's another from molecule, and could decompose it through carbonyl group and this type of on ketone, and as well carbonyl group and ketone here, and produce hydrogen peroxide, which is really, really good. So the idea of the mechanism is becoming for us extremely important to look about what happened to the tetroxide. Okay, this is the peroxide, which is decay mechanism. So in other words, you have a Bennett type of mechanism in the previous slide. I'm sorry. We have the Bennett mechanism, and as well we have as well the decomposition of these materials. So it's a lot of radiation chemistry involved in this type of reaction here. Other important things, of course, which is what really surprised to us. I mean, and then when we start looking into it, the electron, especially in the presence of water, as you know, it produces hydrated electrons, which is really good. We thought hydrated electron is going to attack attack directly the polyester resin. But as well, if you think about it, since there's a lot of oxygen there, hydrated electron that react with the oxygen to produce what they call it the superoxide, O2 minus. So O2 peroxide is very well known here to us. So the superoxide literally again attack the resin. So we are using now the not just the hydroxyl radicals, not the hydrated electron, but as well as the superoxide, the O2- to attack. And this is one of the partial bond reaction of this, and that's how you see how they as well induce the composition here for the things. So that's this is they call it substitution reaction with the, probably if you are an organic chemist, you know what they're talking about, SN2 substitution reactions to the carbonyl group. Yeah. One of the important things which we found, it is a lot of results here, but I chosen only one of them. This resin is a tough one, very, very tough one. In the presence of water, so the issue of it is by the way, it is N, but it's really cross-linked N. It's not really it's a real resin, but despite this cross-linked, which is a tetraphthalic polyester resin, which is one of the best one for preventing corrosion or protect steel and the other metal from corrosion. So that's why it's very heavily cross-linked. Okay, and despite the fact there is a lot of maleic hydride, phthalic anhydride, phthalic acid, and propylene, those guys here, those impurities in that resin undergo polymerization. So still it works against you, but still with that one we achieve a fantastic. Yeah. Okay, so anyway, in final remarks, despite the presence of radiation protective phenyl group in the polyester backbone, phenyl polyester network can be scissions and produce free radicals, and that of course enhance the decompositions and the recycling. And we are really relying again on the hydroxyl radicals as a very important species to attack. And of course, shows as well high dose rate with the pulse electron beam accelerator impede the polymerization of the vinyl group. So this is one of the issue which is we have the issue between the dose rate and the effect of the dose rate on the scission of these. I like to acknowledge, of course, the Department of Energy, and especially especially Oak Ridge National Lab Department, and as well, of course, as well we have to. I like to as well to express my thanks to the geosciences and biosciences under the contract with the Brookhaven National Lab. With that, thank you so much for the listening, and I'm ready for you. Thank you. Hello. Can you hear me?
Sir, yes. Thank you for your presentations and collaborations. Can you hear me?
Yeah, I could hear you very well. Yeah.
Thank you for your presentation.
Thank you. You're welcome. Thank you so much for your kind attention.
One question.
Mohammed. Andrzej is here on this side, so nice to see you and very interesting. Congratulations on previous and also on this one presentation. But after degradation, as we are just discussing here, some application of different technologies, so you degrade this scrap from the ship, and what later on? How they want to use it?
Angie, it's always nice talking to you. I'm so happy that you are here. Absolutely. This is the first step. This is what they call the construction steps. The second step, it is the construction. So what we are doing actually, we are producing now really oligo at the moment, okay, with this one. And these oligomers going to be ready for different type of synthesis. The issue was with those polyester, they dump them really in the soil, and they are very, very polluting the soil and the things. So the idea now, it is the deconstruction at the moment to get oligomers from them, and we get a very good oligomers, and then after that we are sending them now as we speak. Actually, some of the oligomers now has been under the synthesis to produce different type of polymers from them. But the one which they are using at the moment is not radiation. They are using some chemical to do some reaction with them to produce different type of resins.
Thank you very much. So we wish you success in further work. Thank you very
Yeah.
much.
Oh, thank you, Sergio. Are you in Ankara or you are in Poland?
Ankara.
Oh, and in Ankara. That's very nice. Okay.
As we're missing you.
Yeah, I couldn't make it. It's been very busy here. Hopefully, I love Ankara. I like to come to Ankara very often.
Thank you, Mr. Al-Sheikli.
You're welcome. Thank you so much.
Çalıştayımızın programı bugünlük bitti. Yarın devam edeceklerle tekrar devam edeceğiz. Pardon.
Recording stopped.